Thank you, Ben. Hello, everybody. As Benjamin mentioned, my name is Haaren. I'm working in Intel in Shannon, and I'm there working on packet optimization, so packet processing optimization, usually DPDK, but also in this case, I've been looking at OVS recently. And what I've been working on is very much just software-centric optimizations. So we're not talking about offloads and things like that today. This is just, let's say, traditional software optimizations, and let's try and make the existing code that's there run faster, run more optimally on the CPU. So this talk is titled Applying SIMD Optimizations to DPCLS. However, there's a couple more angles to it, so I'll jump straight in. What we're going to cover today is we're going to have a really nice and brief introduction on vectorization, a really nice brief introduction on the miniflow data structure. So I wasn't going to do a show of hands because it's a bit cliche, but it would actually quite help my presentation if I can understand who here in the room has coded something to do with a struct miniflow. Are people familiar with what that data structure actually looks like? Okay, I would say about 1 in every 15 or so people. Thank you. What I'll do is I'll talk a little bit about that. I believe we have a little time more, perhaps, based on the last talk ending a touch shorter. So I'll talk about that a bit more because I think it's worth spreading that knowledge in the community so that we all understand how the internal matching of packets and tables actually occurs inside OVS. So essentially, what is the code or the pattern matching that's going on in the background behind OVS? How does that work? And particularly from a performance point of view, what's really happening there? So that's the miniflow data structure. I'll talk briefly about the Datapath Classifier as well. So that's essentially, we heard in the last talk, a really nice presentation on the megaflow. So that was the blue line in a lot of those graphs. The megaflow is the equivalent of the Datapath Classifier in this presentation. So they are the same thing. The Datapath Classifier, or DPCLS for short, is the implementation of the megaflow concept, shall we say. So the DPCLS, or the Datapath Classifier, will focus on what that does, what it tries to achieve in order to match packets and rules and subtables. So I'll give an overview of roughly what we're doing there. I will keep it a bit simplified because it's these tuple space search algorithms, which is ultimately what DPCLS or the megaflow is. It's quite a complex topic, so I've stripped it down to the essentials as what's required to understand the SIMD optimizations or vectorization optimizations that the core of this talk is about. So the next big bullet there is AVX-512 DPCLS. So what we'll focus on there is vectorization or SIMD, and I'll talk about exactly what that is on the next slide. An implementation of the Datapath Classifier of our megaflow rule matching in vectorized code. And I'll talk about some of the benefits and things that we can get there. I won't go into this at a code level, so vectorized code can be a little bit hard to consume, particularly if you're not familiar with it, or at least somewhat experienced. So I've done up some graphics to talk through that, and hopefully I can give you a graphical overview of what a vectorized version of the Datapath Classifier looks like, even if we don't look at it at a code for, line for line of code or assembly instruction level, then hopefully we can give you a graphical overview of what is occurring. And then towards the end, I'll talk about some future work that I'd like to get into. So let's jump straight in. If we're talking about vectorization or applying SIMD optimizations, so vectorization and SIMD, I kind of use the terms interchangeably. They're ultimately the same thing. And really what it boils down to is trying to do more work per CPU cycle. SIMD is an acronym. It stands for Single Instruction Multiple Data, and really what that means is that in one CPU cycle, we operate on registers that are wider, and we perform the same instruction. So in one example would be to add a number on this wider register and another wider register, and that all happens in one clock cycle. So wider registers means more work gets done. And that's where vectorization comes from, and it's used extensively in the DPDK PMDs, where we can achieve really, really high rates of work being done per CPU cycle. So it's a way of optimizing CPU-bound parts of your program. That's ultimately where vectorization is a very good fit. So in this case, I'll talk about a specific instruction set for vectorization. So AVX, the Advanced Vector Extensions, is one part of the IA-x86 ISA, so instruction set, which is operating at 512 bits wide. It's codenamed kind of AVX-512. So in this particular implement or instruction set, we have 5 12-bit wide registers. So what that basically means is 64 bytes, which most of you are probably familiar with, is also one cache line. So it's a very wide SIMD register. We can put a whole lot of data into these registers, and then we can operate on things in parallel. So again, the main core of vectorization is to get a lot of work done in one instruction, in one CPU cycle. So improve the amount of work you can do per cycle is kind of a concept here. With that, we break these really wide registers. So these registers are 512 bits wide. We break those into what I call lanes. And the lanes concept allows us to operate on, for example, multiple packets in parallel. So instead of loading one packet into one register and then operating with this one register representing one packet, what we're going to do is we're going to split this one really large register into smaller lanes, into smaller chunks. And in this case, we'll use 8 lanes, which means that we have 8 times 64 bits. Now, as most of you are aware, on modern a lot of common platforms today, we have 64-bit architectures, which means that our pointers are 64 bits wide, and a lot of common data structures use UN64s or 64 bits of data to represent certain things. And for those familiar with the miniflow, you'll be thinking, yes, we store particular elements of data in the miniflow as a UN64. And for that reason, it's a really nice fit here that we have 8 lanes, and each one of those is a 64-bit integer. So we can actually start to do some optimizations based on that, and I'll talk about that more in some future slides. For now, if you're thinking, hey, Harry, this is kind of getting a little bit too technical, consider we have 8 lanes inside one register, and each one of those lanes represents a packet. So ultimately, we have 8 packets in one register, and we're going to operate on those packets in parallel in this case. So that's a brief summary of this. So I'll skip on to this miniflow data structure. I think this is kind of where there's a graphical way of depicting what this data structure looks like. So on the bottom right, we see a blue box there. I'm going to talk about the miniflow more conceptually than in its implementation. So the blocks represent the values of a piece of metadata. What am I talking about here? So IPv4 destination IP has been highlighted here in the green box. And basically, this is the actual IP value. So it's a figure like 10002 in a lot of examples from earlier today. So that's where that data is stored. If you follow the green arrow along and back to the side, we have a part that I'm calling the bits. And the bits indicate what metadata is present in this whole miniflow data structure. So this particular bit, I have one highlighted in blue and slightly bigger. From this, that bit indicates that the field following the arrow, the block there, is of a particular type of metadata. So this is the main concept to grasp from this slide. Each bit in the bits array has a particular meaning, and when that bit is set, it means the block to the right of it is representing that type of data. And this is the core concept, the core logic behind our tuple space search in the Megaflow. So we'll see more of this throughout the presentation, and I'd be very happy to take questions on it at the end. So for now, we'll continue on. Just remember that the bits represent the metadata, like what the block on the right represents. And if you follow the arrow, we can see the relationship between the bits and the blocks. Moving on from there, we'll talk about the Datapath Classifier and really what that's trying to achieve. The first thing, actually, I'll skip back one slide because I missed one point here. The miniflow represents both packets and subtables. In this case, we can assume a subtable to mean the concept which a bunch of rules are inside one table, but also the rule itself has a miniflow. So miniflows are kind of used for 3 purposes. And ultimately, they're always used as a structure to represent metadata about packets or about a table or about a rule. So the real tuple space search is the marriage of these 3 components, which is the packet itself, the subtable, and the rule inside that subtable. They all have a miniflow, and what we're doing is we're matching those 3. So in this case, I'm going to leave the rule component out for the sake of simplicity for this talk. I think it's not required to understand the SIMD optimizations I'll talk about next. But the core concept here is that what we do is for each subtable that we want to match a packet against, we're going to iterate every bit that's set in that subtable. So we can see here the subtable is highlighted as the top large gray box with the blue tag on the side. So that's our subtable, and it has 2 bits set in the bits array. And to the right of there, we can see that there are 2 blocks filled in, one green, one yellow, and those represent the metadata, so the actual, the value of the IP address, we'll say. So not the fact that an IPv4 address is present, that's what the bit represents, and the block represents the actual 10.0.0.2 value of that IPv4 address. And what we do when we say we want to match this packet against a subtable is we search for similar fields in the packet. And the important thing to note here is that the packet could have a different set of metadata present. So the bits set in the packet could not be a one-to-one correspondence, or in almost certainty will not be the same. So we will need to kind of do a search of sorts to find where the metadata is contained inside the packet. So in the diagram here, we can see that we're trying to match the green boxes together. That's the core concept. And similarly for the yellow box, we want to find the VLAN, and we want to find that similar corresponding piece of metadata inside the packet, but it won't be at the same location in this array. So by doing this, the miniflow is a bit of a kind of a generic data structure that can contain various different things, and the bits that are set represent what metadata is contained in the miniflow itself. I'm looking at a lot of blank faces here, so I hope I'm making this clear. The core is that when we do a match between a packet and a subtable, we're trying to find the same colored boxes. We're trying to match the metadata so that we can compare those and that we can later apply operations such as hashing or table lookups based on that. So in this example, we can see that we're matching the IPv4 from the subtable and the IPv4 from the packet, and then we're going to apply a masking operation or a bitwise AND to those 2 bits of data. Let's move on. Let's look at how the current code implements this kind of search between the packet and between the subtable. So the algorithm is described as such that for each bit that's set in the subtable, so again, the subtable is the top gray box here, for each bit set in the left-hand side of that, the bits array, we have a block of metadata on the right. So the first bit set is if we look, there's 2 bits set, it's one of those. And I have the green box labeled with a large 1 in red. That's the first block of metadata that we're trying to match inside the packet. And the current code basically takes what I'm kind of calling a linear scan. So it just starts from block 0 and checks, is this the metadata that I'm looking for? And if it's not, it will move to the next block of metadata. So we can see here that we skip, I grayed out the IPv4 source IP, and the red arrow moves to the next block, indicating we're now checking this next block for, is it the same? And in this case, it is. So it is the green block that we were looking for. When we move on to the second bit in the subtable, in this case, the VLAN, or the yellow block, marked with the blue number 2, when we move on to that, we continue searching from where we left off in looking for our first block. And this is a kind of a key or important part to understand, that there's a dependency when we start the second block or the second piece of metadata on the result or the location where we stopped searching for the first. In terms of code, we often refer to loop-carried dependencies. This is essentially kind of a loop-carried dependency of sort. So there's a dependency that we need to finish the red search, in this case, for the block number 1, before we can move on to block number 2. And from there on, we will find our VLAN or our yellow block, and then we've essentially completed the search for the metadata required by this subtable. So it's a way of searching, and the pattern here is to move linearly from block to block, and wherever we're done, we'll continue searching from. So it's optimized in the sense of we don't start again from the very start, but also there is this loop-carried dependency, which is somewhat of a performance hindrance, because it means that we need to complete iteration 1 before we can start iteration 2. And keep that concept in mind. I'll talk about it now on the next slides. So a really quick rehash on what I was talking about, the bits corresponding to the blocks. If we look at the packet data, look at the smallest little blue arrow in the middle, we can see there's a 1-bit set, and it points at the first block available in the blocks. If we look at the next bit set, that's the green box that we've been looking for. The next bit, so the third biggest arrow, is pointing to the MAC source, and then the very largest outer arrow is the 4th bit set, which points at the 4th item in that blocks array. So this is a kind of a concept that we need to build up, that each bit in this packet's bits component represents or indicates what metadata is present later. Because what we're going to do is we're going to utilize this property of the miniflow. So this is really a core concept of the miniflow data structure. How this works, this is the algorithm in how we traverse and how we search the miniflow today. But what if we were to make use of the property I've just described with the arrows here to create a different implementation of that same search? And that's what this slide currently on the show here will do. So I'll talk through this kind of slowly, and we can see what we could do with this concept on the next slide in terms of vectorization. So this slide, I've titled it pop count. It's kind of the key enabler of this approach. If we look at the top left, we see this mask block that has arrived. So previously, we just had arrows. Now we see this mask component. If we create a bit mask that's set for zeros all the way to the bit that we have, and ones underneath. So this red box called mask would be all 1, and everything above there would be zeros. Then we can create a mask which will only allow the bits to pass through if the bit is set in the packet. What I'm trying to say here is there's a way that we can strip off the bits below the one we're searching for, and then we can do a population count or a pop count. For those not familiar with the pop count concept, it's a way of understanding how many 1 bits are in a number. So it's not a binary representation of a number, we're just counting how many 1s were in this. The really nice thing here is when we've done this mask and we pass the result of that mask operation with the packet miniflow bits to pop count, it actually tells us what index to access the array of blocks. I'm going to say that again in a second. But if we follow the mask itself is going to give us a number of bits. When we do the pop count, that gives us an integer based on the number of 1 bits that were set. And that integer result from the pop count is the array or the index to the array of blocks. So this packet has 4 blocks being shown. If we access that at array index 3, of course 0-based arrays in this case, then we get to the 4th block, which is the yellow VLAN TCI that we were looking for. If we go back to the mask, we can actually see that there were 3 1 bits in the packet miniflow. So there's a correspondence between the number of bits set below the one we're searching for and the array index to access the blocks with. That's the core enabler of this optimization. That we remove the loop carry dependency that I mentioned 2 or 3 slides ago, because we now no longer need to search for the first part and find the first part before starting the second. With this mask generation technique, we can actually look up all of these in parallel. They're no longer loop dependent, or they're no longer dependent on each other. So with that optimization in place, what we actually end up with is a way to generate any address or any index into that array without any previous knowledge of the miniflow. That removal of this loop carry dependency enables us to do much more vectorization. So in vectorization, a common problem is that you need previous results to be able to calculate the next results, which stops you from parallelizing certain types of work. This masking approach, on the other hand, allows us to generate those indexes into arrays in parallel. So we've removed this dependency, which means that we can actually vectorize this part of the OVS searching and packet matching. Okay, with this pop count approach, we can do a vectorized implementation. So as I said, I'm not going to show up the exact vectorized code itself, but we'll look at a graphical depiction of what we're going to do. And I'll spend the next 6 minutes and 52 seconds explaining this. The core concept between this page here with the pop count, where we have a subtable and a packet, is identical to this page, where at the very top we still see the same subtable, and the first packet, packet 0, is still the same packet. So fundamentally, the operations that this vectorized slide is showing is identical to the previous slide. There's no new concept. The only thing that I'm introducing here is rather than doing this for one subtable and one packet at a time, we're now going to do it for one subtable, but we're going to look up 8 packets in parallel inside this vectorized register. So how do we do that is a good question. And it's a little bit tricky. I've tried to present it as graphically as I could here so I can kind of talk through it on the slides. If we start in the top right, you see this gather unit 0 miniflow. So vertically, and in this case with vertically what I mean is across 8 different packets, what we're going to do is we're going to load the first 64 bits of each packet bits. So that blue box that's shown here on the slide is being loaded, and it's not contiguous in memory. They're in different places, but our gather instruction, which is part of this AVX-512 instructions, is exactly that. It's going to pull this data into a register. The next, we see this kind of corner-shaped part for each bit in the subtable unit, which is exactly the same as we talked about in our previous slide, like this, where we iterate the bits of the subtable. What we're going to do is we're going to generate a lower than mask. Again, referring to the previous slide, we generated this mask. We're going to do a pop count, which is going to do the exact same as a scalar pop count. We're going to do a SIMD version so that we can do these lanes in parallel. With that pop count index, we're going to call the gather instruction again, but we're going to load up the different blocks from various indexes in that block array based on each packet. So again, it's the SIMD pop count and doing that number of 1 bits to index calculation in the register itself that enables this gather operation to then work as a next step in parallel. And the fact that we don't have that loop carried dependency or that dependency between looking for the first block and the second block makes this code much simpler. After that, we can do the mask with the subtable block. That's ultimately the bit mask and operation I mentioned earlier. And then we can store the data for processing later down the DPCLS pipeline. So this has been a whirlwind tour of what doing a vectorized version of DPCLS, at least the initial stages of DPCLS, looks like. At this point, we could store the data and then do a scalar hash, but we could take the concept further and apply scalar hash or vectorized hashing as well after having this data loaded in our vector registers. After that, there's a hash table lookup and there's a rule verify stage. Those can also be vectorized, and I do intend to also upstream patches to the community which perform exactly those things. For the sake of brevity in this talk, I'll move on. I think this has given you an introduction or a kind of an insight into what the vectorization of DPCLS looks like, and that it's a very possible thing to do. And the benefit we get here is ultimately we get 8 packets done at the same time. So future work, how can we enable this in OVS as a community? How can we look at this? Of course, not every CPU has this AVX-512 instruction set, so that's something that we need to work with, and we need to be able to kind of selectively enable this or disable it based on the CPU features that are available. My suggestion here, and I've sent a patch set to the mailing list to do this, I'll bring up the patchwork ID on my last slide. The solution here, I think, is to add a function pointer per subtable. And the reason for this is that it allows very flexible selection of our implementation of DPCLS. So do we want to use the vectorized version or the existing scalar version? But it also allows us to use a bit more context to select this miniflow or the exact implementation. And this actually will benefit our scalar code too, because if we have a known number of bits, for example, 6 bits that always get hashed, then we can have a specialized version of that function that the compiler actually unrolls for us at compile time, and it basically means we get loop unrolling in our final binary. We get less branch mispredicts. We get more high performance code just based on the fact that we have this function pointer in our code base. So there's benefits there. There are probably some drawbacks in terms of we need to enable this. We need to make sure that the community understand why they're there. This is used extensively in DPDK in our Pulmo drivers already. It is a very highly performant solution. The important things are to make some design decisions correctly at the start. If there's anyone with concerns, I will be around for today and tomorrow, and I'd really like to discuss these things. We had a brilliant talk earlier by Andrew on cache utilization of EMC, SMC, and DPCLS, so I'll leave that topic aside for now and finish with 2 more bullets. So I think from a somewhat outside developer to OVS community trying to vectorize and optimize DPCLS, it's been very difficult to get a benchmark which gives me a definitive answer to did my code improve performance, yes or no. There's a lot of use cases, I'm aware. There's a lot of different types of scenarios which we can deploy. And having well-defined use cases where a developer like myself could come and optimize against would be immensely helpful. So at this call to action for the community would be to contribute a use case you have X amount of subtables, this type of traffic pattern. If you can share that data with the community, then the community can really use that in driving optimizations like what I've shown today. Without that information, I'm really flying blind. It's impossible to understand if this optimization would eventually be accepted upstream or not. So that's kind of where from a software optimization point of view, I'm looking from. And finally, in terms of enabling the AVX-512 mode, I was going to suggest a single kind of button that we can press, go faster, and use CPU features to do this. That hopefully makes it a usable feature, so not very difficult for people deploying OVS to understand, to use, reducing complexity, improving usability. That's kind of the goal here. And it could enable things like optimized DPCLS functions or other CPU-specific optimizations. So with that, I'll say thank you very much for listening to me. I hope it's been interesting. If you have questions, please do come forward to the microphones. My email is here. If you'd like to reach out, feel free. And I have the patchwork series here as well. So if you'd like to look at the patches that implement these function pointers into the DPCLS subtables, that code is existing. There's also an optimization patch there for the rule matches key, which Andrew very aptly mentioned in the previous talk. So there's some things there that we can work on. So with that, if there's questions, please.
Yeah, let's thank our speaker. And if there are questions, please come to the mics. A cool hack. So I have a question to start out. So the miniflow data structure was also what I think of as a cool hack, but there's nothing essential in the exact structure it uses. Would there be modifications to the data structure or an alternative way to express it that would be more amenable to SIMD optimization?
Initially, when I started out looking at this, I would have said yes. Right now, I'm not so sure. It has a very generic property because it can represent the metadata in different locations. It's very powerful and it's actually quite cache friendly. So a lot of the metadata gets very compacted onto the same cache line as the miniflow itself. So there is some CPU overhead in terms of understanding which metadata is represented at which index in this blocks array. But because we can do this mask and pop count trick, that's literally 3 or 4 cycles now to do this if we can get a few packets in parallel. So I think it's quite a beautiful data structure from a SIMD point of view with these understandings of that we can use the pop count to find the index.
Yeah, it's a sort of a strange data structure from a CPU optimization perspective because it performs very differently when you have a CPU with a pop count instruction versus one that doesn't.
So interestingly, in the SIMD pop count, we don't actually use the pop count instruction because there is no currently SIMD vectorized pop count instruction. So what we do is we emulate that using ordinary integer adds and multiplies, which essentially could be done on any CPU at all. So that's how the vectorized version of the SIMD pop count works. Yeah.
All right, that's good to know. Justin, do you have a question?
Yeah, I was just curious. I'm sympathetic to the, when we've tried to make performance optimizations in the past, it is very difficult because you can have very different characteristics depending on what kind of flows are loaded. You could use something like oven to produce some set of flows, but obviously there's a lot of variability there depending on what you configure. But do you have any performance numbers of just some basic set just to kind of give an idea? And then also, how much complexity does this add to the code base?
So brilliant questions. I'll talk about the performance numbers in later, or we'll chat offline perhaps. In terms of complexity, that's another really beautiful thing about these function pointers, that if we use these function pointers, then we can basically split out the complexity. So we keep the current scalar code path that exists, that everyone's familiar with, and we leave that as the default option. So we don't want to change or break anything here. That's not the goal. If we have these function pointers, then we can redirect functionality if CPUs allow it. And that basically allows CPU vendors, for example, Intel that I'm working for, to optimize for particular CPUs and to take on that maintenance burden in doing so. So it does complicate the code base a tiny bit in terms of this function pointer call, but I would argue it's not, like the gain we get is huge. And for anyone who's curious, I'd love to talk more about the benefits for scalar code and the loop unrolling specialized version of functions. So there's actually quite a lot we can do if we know the context of what work this loop needs to do. So because the loop is no longer generic, it's specified for a specific subtable, we can apply scalar optimizations there for that too. So it does create, it's change. Change is ultimately complex because it means you need to learn new stuff. But the performance gains we can get are significant.
And do you have some concept of what those gains are?
Approximately. So in very simple testing on my own network, so this is really, really simple single flow type stuff, I've seen somewhere 20-25%. For specific things, we have some other optimizations in the pipeline, so I do encourage run the tests yourself, try these things. Also benchmark just the function pointers on their own. So see, does that degrade performance? In my testing, I've seen 0 degradation in performance, but even that is very valuable feedback to folks. So thanks for your question.
All right, let's thank our speaker one more time.
We'll talk offline. All right, thank you.